Hi guys, it's Mrs. Allison. Today we are going to focus on polar coordinates, equations, and derivatives. Now, you should have seen polar coordinates last year, hopefully. But what they are is just a different type of coordinate system. And we've looked at coordinate systems since you started algebra, maybe even before that when you were younger and would start on maps and graphs. But a coordinate system is just a way to define a point in space. Okay, so some point in space is defined by a coordinate system. Now, when you looked at maps when you were in elementary school, you maybe would go across the top and there'd be letters, and down the side and there'd be numbers, and you'd say, okay, the bank is at A3. And that's a point in space. It's a coordinate system. Same thing is true in algebra when we begin and we start with the idea of ordered pairs. And an ordered pair, xy, is really just defining something that is x units over and y units up. It's a point in space. Well, what the other option is that we have is what we call polar coordinates. And polar coordinates, again, defines a point in space. We have two parts to polar coordinates. So with the Cartesian coordinate system, which is what this xy is, we just have the x component and the y component. When we're dealing with polar coordinate system, our ordered pairs are not going to be xy any longer. They are going to be the ordered pair r, theta. And where r, theta comes from is it comes from first the number of radii out. I just call it the rings because if you look at a polar grid, there's multiple rings. So this r value, this first coordinate, is represented by how many radius or radii we go out to get to our point, basically what ring it's on, and then our theta value. And our theta value is the angle from standard position. And if you remember from before, standard position, we would have done this in unit circles, standard position starts on the positive x-axis, and it's the angle that is traced going in a clockwise motion if it's negative, or a counterclockwise motion if it's positive. Okay, so this angle here is my theta. Now, this particular point on my coordinate system, and I'm going to go ahead and erase all that I've drawn, this particular point in my coordinate system could actually have multiple names. If we start with maybe the most obvious name for this particular point, we might call this 4 and then pi over 4. 4 because it is 1, 2, 3, 4 rings out, 4 radii out. And then pi over 4, I'm just estimating that it's about halfway between the two quadrants. So 4 comma pi over 4 is one of my ordered pairs that represents this point. Now, if you remember from Algebra 2 trig, we talked about coterminal angles. And a coterminal angle to this that has the same measure that we just found may be 4 negative 7 pi over 4. Well, 4 because it's still 4 radii out, and negative 7 pi over 4 because if I trace this in the negative direction, I end up back at that exact point. So 4 negative 7 pi over 4 would be another point. Now there's a couple other that are a little bit funky that we haven't seen before, and that's dealing with the fact that our ring, our radius, our r value needs to be positive or is expressed positively most of the time. For example, we wouldn't ever say, hey, my radius is 4 this way, but you know what, or 1 this way, I guess I drew 1, and negative 1 going this way. We don't say that. It's still a radius of 1. And so one of the points that this could represent is actually the point negative 4, 5 pi over 4. Let's think about why. If I were to go to the angle of 5 pi over 4, 5 pi over 4 would be this angle right here. But because my radius is not negative, if we say -4, it's going to take something that's on the angle of 5 pi over 4 and mirror image it across the line, or across the origin rather. And so this would be my point, -4, 5 pi over 4. Now, just like we talked about negative coterminal angles, we agree that this would be 5 pi over 4, this point right here. But with if we went in the negative direction, that angle would actually be -3 pi over 4. So if I make this a -4 for my r value and a -3 pi over 4, it will bounce this point right back to the point that we had notated for us. So keep in mind, they are points in space, but there are more options for polar than there are for the Cartesian coordinate. Okay, but we need to now be able to convert between Cartesian and polar coordinates. And the way we're going to do that is we're going to picture this graph here, something like we just had drawn. And I want us to think back to geometry just a little bit. There's a few formulas we need to know. One, if I'm looking at this r value right here, then I could find that r value by using the Pythagorean Theorem. Do you agree with me that what this says is that x squared plus y squared equals r squared? Okay, now let's deal with that angle. That angle of theta gives me some more clues. Think back to trig again. Do you remember, do you remember when we did trig and we did SOHCAHTOA? Do you feel comfortable in me saying that the sine of theta equals y over r, and then the cosine of theta equals x over r, or adjacent over hypotenuse? Do you agree with those statements? Okay. And you may even agree with the fact that the tangent of theta is y over x. That's perfect. Now, what we're going to do with this sine and cosine to be able to make conversions is rewrite it so we have one is x equals and one is y equals. So we get the equation x equals r cos theta and y equals r sine theta. And using these helps me convert between Cartesian and polar. Let's work on some conversions. So let's convert 5 pi over 6 to rectangular coordinates. What this means is this 2 represents r, and this 5 pi over 6 represents theta. And so the easiest way that we're going to be able to do this is if I know my r and my theta, I'm going to go up to my equations to find x and y, which are the Cartesian coordinates or rectangular coordinates. I'm going to use the two formulas x equals r cos theta and y equals r sine theta. So let's look at what that looks like. X equals r cos theta. So x equals, in our case, 2 times the cosine of 5 pi over 6. So 2 times the cosine of 5 pi over 6. Well, the cosine of 5 pi over 6 is 5 pi over 6, and cosine would be -√3 over 2. So I'd have 2 times -√3 over 2 equals x. So x would equal -√3. Now let's repeat that for the y. Y equals r sine theta. So in our case, y equals 2 times the sine of 5 pi over 6. 2 times the sine of 5 pi over 6, I would get 2 times positive 1/2, which gives me y is 1. So my rectangular coordinates would be the ordered pair -√3, 1. Now, since I don't have a polar graph down here, I'm just going to scroll up just so you can see what this looks like. And if we go back to this picture up here, let's just erase what's there. 2, 5 pi over 6. 2 rings out, and 5 pi over 6 is not quite pi. So 5 pi over 6 is somewhere right here. does it make sense if we were to put this on a rectangular coordinate system that this might be the ordered pair negative root 3, which is more than 1 but less than 2, so negative 1.7 maybe. Don't have my calculator in front of me. And positive 1. Does that make sense where that point is at, that could be the coordinate? And yeah, we can see that makes sense where that point is. All right, so to do this in reverse, let's try it in reverse. This time, let's convert the ordered pair 3, negative 3 into polar coordinates. And when we convert into polar coordinates, we need to find r and theta. And the easiest formulas to use to find those are the x squared plus y squared equals r squared and the tangent of theta. So see if you can substitute it in and figure it out. All right, if I plug this in, let's start with the x squared plus y squared equals r squared. So in our problem, we would have 9 plus 9, because negative 3 squared plus negative 3 squared would be 9 plus 9 equals r squared. And so we get r squared equals 18, which means r equals plus or minus square root of 18. Let's simplify that just a little bit. Plus or minus, that would be 3 root 2. Okay, then we've got the tangent. Well, we've got the tangent of theta, and it needs to equal my y over my x, so negative 3 divided by 3. So I get the tangent of theta equals negative 1. And if I go and solve for theta here, I would get 3 pi over 4, 7 pi over 4, negative pi over 4. We could go on for an infinite number of points if we start looking at all our coterminal angles. But the key is I need to watch my quadrant and figure out where this point might be. So the point 3, negative 3, if we looked at it on a rectangular coordinate system, 3, negative 3 would be somewhere down here. Maybe not drawn to scale. 3, negative 3 would be right here, approximately. So I need to figure out what coordinates that might be. Now I know the x-coordinate could be plus or minus 3 root 2. So if we start with the fact that it's a positive radius, let's start with 3 root 2. Then the degrees have to match that angle of rotation. And so I would say then that since it's on the 45, this would be 7 pi over 4. I'm not sure why there's a comma with the 3 root 2. So 3 root 2 comma 7 pi over 4. I may also be able to say that this point would be positive 3 root 2 comma negative pi over 4. Because that would be in that same quadrant. It would just be the negative angle. But what would this point look like if it were actually a negative ring, a negative radius? So negative 3 root 2. What angle would it be? Well, to be on that same trajectory, that negative angle or that angle would need to be 3 pi over 4. And then we could also say that negative 3 root 2 could be the negative 5 pi over 4. And all of these would be examples that convert our 3 negative root 3 into polar coordinates. It's helpful also to be able to convert equations from rectangular to polar and vice versa. So let's start with, I'm going to start with a more complicated one initially. If we have an equation like y equals 2x plus 1, typically when we go to convert our equations, the first thing that we're going to do is we're going to substitute in for y and x. So in this problem, we might say r sine theta equals 2 times r cos theta plus 1. And then my goal is typically to get it to be an r equals equation or a theta equals equation if I have that, if there's one that's going to be easy to solve for. And I can see that while maybe not initially easy to look at, may not be your first response, if I gather all of my r's and thetas on one side of the equation, meaning I have r sine theta minus 2r cos theta equals 1. I can factor out an r. And then I can solve for r, and my equation is r equals 1 over sine theta minus 2 cos theta. Now, do I know how to graph that better than I know how to graph y equals 2x plus 1? No, I don't. And in fact, in a little bit, we'll look at how to graph these. I don't actually want you to have that, that's not the main focus for the polar stuff. But understanding where graphs come from are important. So we'll look at that in just a second. But this is how we can convert those equations. And as we move further on in math, there's going to be some techniques in differential equations when it's going to be much easier to convert to polar to be able to solve equations than it would be in the rectangular form. All right, try the next one and see if you can solve this in terms of r. So hit pause and come back. All right, hopefully you had a chance to look at this. If we make our substitutions in for y, we would have r sine theta equals 4. And if my goal is to get r by itself, I would just divide both sides by the sine of theta. Or maybe I would rewrite it to say r equals 4 cosecant theta. And this would be your answer. You have just converted the equation y equals 4 into polar form. Okay, and sometimes it's really easy to make sense of these conversions. This next one, we should be able to make sense of this conversion and why it is what it is. So let's look at C and see if you can come up with maybe what you might substitute in for. All right, hopefully you had a chance to try it. If your first thought is to substitute in r sine theta and r cos theta for x and y, that will certainly work. But it's going to be a little bit longer. Do you remember up above when we were looking at our conversions? We said that x squared plus y squared could be rewritten. It can be rewritten to be r squared. So really we have r squared equals 16. And if I solve that, I get r equals plus or minus 4, but we really only focus on 4. Well, let's talk about what this might look like on a polar graph. All we know is r is 4. Well, let's look back up top, and if all the places where r was 4 were the places that were around the fourth ring, the fourth circle, radius of 4, wouldn't that make sense that that would be r equals 4? And if we go back and look at our original equation, x squared plus y squared equals 16, what would you expect that shape to look like? Hopefully a circle. And so it makes sense that the equation r equals 4 is in fact my answer. All right, let's go backwards. Let's try this in reverse. Let's convert the following equations from polar to rectangular. Now, I'm going to give you the most complicated one first, just like we did before. And I'm going to tell you on this one, and it seems strange to do, but I don't know anything. I don't know anything about just 2 cos theta. I don't know anything about just r. But I do know some stuff about r squared. And so if I were to multiply both sides by r, so we get r squared equals 2r cos theta. Now I can make substitutions in place of the things that we know. We just said above that r squared is equal to x squared plus y squared. And we know that 2r cos theta can be rewritten as 2x. Now, if we wanted to, this is an equation. It's not very helpful. None of us know what this looks like. So let's do some manipulation. If we subtract the 2x, and then I complete the square. So I would divide this b by 2 and add that back, and I'm going to add it back to the other side. So I get plus y squared. I can rewrite this to be x minus 1 squared plus y squared equals 1. What is this? This is a circle with a radius of 1, whose center is the ordered pair 1, 0. And when we graph 2 cos theta, and we're going to do this in just a second, look at an example of this, you're going to see that this is in fact a circle that has been shifted to the right 1. Okay, so let's try B, or maybe hit pause and try B. See if you can try it. All right, this one's a little funky. Theta equals 3 pi over 4. Well, I don't really have any information about just theta, but I do know stuff about the tangent of theta, but this doesn't say tangent of theta. So, what if I take the tangent of both sides? So let's rewrite this as the tangent of theta equals the tangent of 3 pi over 4. So simplifying, we'd get the tangent of theta equals negative 1. Well, we know what the tangent of theta is. We know that the tangent of theta is y over x. And if I maybe rewrite this, I get y equals negative 1 x. And this is the Cartesian graph, or the rectangular graph, of theta equals 3 pi over 4. Well, let's think about theta equals 3 pi over 4. If I were to draw a picture of this, and granted I don't have all my rings down, that's okay. 3 pi over 4 would be a line, or would be right here. So this would be my angle of 3 pi over 4. Does it make sense that I have the equation y equals negative x as the same equation as theta equals 3 pi over 4? Yeah, they're both in the same place. All right, so hit pause and try this last one. Okay. Well, r is not super helpful unless it's related to sine or cosine. So let's rewrite this as r equals 1 over sine theta. And then if I manipulate this just a little bit, I get r sine theta equals 1. And we know that r sine theta is just y, so y equals 1 is my rectangular equation. Hopefully that rings some bells a little bit. If not, you may need to hit pause, rewatch that again. I went through kind of quickly. But you need to be able to manipulate equations back and forth between polar and rectangular, or polar and Cartesian. So now let's move on and talk about the derivatives. I think you're going to see that these derivatives are going to be very similar to what we did with parametric equations as well. So if the function is r equals f of theta, some function relating r and theta, then dr d theta means the change in r with respect to theta. That makes sense. But the problem is when we talk about slope, slope is dy dx. So can we rewrite dy dx so that it deals in terms of thetas and r's? Kind of, we can. Now, what we're going to use is we are going to use a process called parameterize. And to parameterize means that we're going to take what we know about y and what we know about x in terms of parametric equations, and then we're going to think about dy dx. dy dx, using the idea of the parametric equations that we did before, can we rewrite dy dx to be dy d theta over dx d theta? Will that give me the same result? So now I need a y function in terms of theta, and I need an x function in terms of theta, because when I divide those two, I will be able to find my slope dy dx. Let's look at an example. This says determine the equation of the tangent line to r equals 3 plus 8 sine theta at theta equals pi over 6. Well, what do we know we need? We know to write an equation of a tangent line, we need a slope. And when we need a slope, we need derivatives. So we're going to start with the equation x equals r cos theta and the equation y equals r sine theta. And what we're going to do is we're going to substitute in place of the r in my equation, we're going to substitute in what I know r to be. In doing this, what you're going to see is we're going to get an equation that is only in terms of x and theta, or is only in terms of y and theta. Now, we set up above that to find the slope, I'm going to do the derivative of y with respect to theta. And derivative of y with respect to theta is going to be, I should have had parentheses around that, is going to be either we need to distribute that sine of theta through, or we just need to use product rule the way it's written. I think I'm going to use product rule the way it's written. So I'm going to find dy d theta. Doing that, I'm going to get dy d theta. Let's see. Derivative of the first would be 8 times the cosine of theta times the second plus the first times the derivative of the second. Derivative sign is cosine. Not sure why I have an extra s in there. And this would be my derivative. Now they did tell us we're doing this at pi over 6. So my theta here is going to be pi over 6. Could I simplify this more? Sure. But if I know I'm plugging in a value, I may as well plug in that value to begin with. So dy d theta, I would have 8 times the cosine of pi over 6. Cosine of pi over 6 is root 3 over 2. Times the sine of pi over 6, which is 1/2, plus 3 plus 8 times the sine. We know the sine. 8 times the sine was 1/2, times the cosine, which is root 3 over 2. And if we simplify this, let's see. This one I'd get 8 over 4 root 3, so it'd be 8 over 4 root 3 would be 2 root 3. And this next one, simplifying, I would get, let's see, we would end up getting, let's go back to the pencil, 3 root 3 over 2, zoom that out, 3 root 3 over 2, plus, that'd be 4 times, plus 4 times root 3 over 2, so that's 7 root 3 over 2, plus 2 root 3. If I combine all those, I think I get 11 root 3 over 2. And there's dy d theta. Now I need to repeat that process because I still haven't even found the slope yet. My job is to find the slope. So now let's do dx d theta. Dx d theta. And if I take the derivative of the first for dx, derivative of the first would be 8 cosine theta times the second minus the first times the derivative of the second, and the derivative of the second would be negative sine. And I'm going to evaluate this at the same value. So I'm going to evaluate this at theta equals pi over 6 as well. So in this first one, we're going to get 8 times root 3 over 2 times root 3 over 2 plus 3 plus 8 sine theta would be 1/2 times the negative sign of theta, and the negative sign of theta would be negative 1/2. So this first expression is going to give me 6, because we'd have 3 times 8, which is 24, divided by 4, which is 6. And this next one is going to give me negative 7/2, which gives me 5/2. So my slope is dy dx, and dy dx would be 11 root 3 over 2 over 5/2, which equals the slope of 11 root 3 over 5. Now, I need to find a point. Well, the point, all I know is theta. So the point that I'm going to do is I'm going to take this theta equals pi over 6, and I'm going to find x of pi over 6 and y of pi over 6, because I need this in rectangular form. So x of pi over 6, I'm going to use the idea of what x equals. This 3 plus 8 sine pi over 6 cosine pi over 6. So 3 plus 8 sine pi over 6 cosine pi over 6. And if we do the math in there, that is going to, I'm just going to cheat just a little bit. It'd be 7 root 3, and you can verify, 7 root 3 over 2. And if we do the same thing for y of pi over 6, we get 7/2. And again, you can verify. So now I have all the information I need. I have a slope, I have an ordered pair, an x and a y, and now I can go write my equation. Let's do it in black. Y equals, let's do it in point slope form actually. Let's do y minus 7/2, that's the y value, equals 11 root 3 over 5 times x minus 7 root 3 over 2. And this is my equation of the tangent line to r equals 3 plus 8 sine theta at theta equals pi over 6. Okay, now I did not put this part on your notes because I just want you to follow along. And I will link the presentation on the next slide, just so if you want to get on and play with it, you can see what it looks like. So hang tight. Okay, if you wanted to get on and play around with the idea of polar graphs, we can do some investigation in this link. So this link, this goo.gl/kjnmzw, will take you to this Desmos activity. And it's actually pretty cool if you want to just play around and look at some of the polar graphs. So we're going to look at both the sine and the cosine. You can see the equations we're going to focus on are the a cos theta and the a sine theta. And let's see if I can make it work. I may not be able to now that I've clicked out of it. Nope, here we go. Okay, so you can see what happens as I change my a value. And we can see that this graph becomes a circle. And remember how in our notes that we just did, we looked at the circle 2 cos theta. So here I'm dealing with sine. So if we look at 2 cos theta, I'm dealing with cosine right now. You can see that this is a circle that has been shifted to the right 1 unit, but not up any. And that's what it looks like. So we could play through all of the different sizes and let it just play, and you can see what it looks like for the cosine. And if we look at the sine, whether we keep that on there or not, the cosine, you can see that this cosine was a circle on the x-axis, but the sine is a circle on the y-axis. And if we change our a value, we can see what really happens. We can play with the b value too, but it doesn't do much in this example. Okay, so those are pretty basic graphs. So I want to go on and just look, and again, you can get in and play with this if you would like. I would like to look at problem set 2 and just turn on one of these graphs. Okay, do I want that one? Nah, we'll turn on just that one. And I'm going to go up to the top and I'm going to slide my A in and out. And you can see it just changes my graph a little bit bigger. And if we go to the N and we change our N, it changes how many petals we have for the polar coordinate. Okay, and that's the cosine graph. And you can see what that looks like. If we go and change it to the sine graph, it does something very similar. Right, and there's the sine graph. And again, you can get in and play with these. I'm just going to turn that one off. And let's look at the next problem set. This one changes things just a little bit. Oops, didn't mean to turn them both on. And if I change my A value, we can see that this graph changes quite a bit. B value, change my B value. N has no impact on this one. N is only on the last one. But what I want to do now is I want to walk you through how we could graph this by hand and where the values come from. Okay, so let's see if I can make this. And the point is not to know how to graph these by hand. I just want to show you where they come from and you can understand where it goes. Polar has direction just like parametric has direction. And if I want to set up a table of values, the table of values that we set up actually looks a little bit different than in XY. I know in X, what we find first, we plug in X to get Y. We're going to do it a little bit differently here. We're going to plug in theta to get our R value. And the way that we're going to do that, or the easiest way to do that, is pick quadrantal angles on the unit circle. So we're going to look at 0, we're going to look at pi over 2, we're going to look at pi, we're going to look at 3 pi over 2 just so you can see what happens, and then 2 pi, and we're going to fill this in. So the equation that we have right now looks like it is, we have the equation, let's go back, R equals A, we chose -1, plus B, we chose 2, sine theta, and that's the equation. That just happens to be the one I landed on. You guys, there's no other reason I chose that, other than that's just what I landed on. If we substitute 0 into this equation for theta, we would have -1 plus 2 times the sine of 0. Well, the sine of 0 is 0, and so we get -1. So at theta equals 0, we get -1. Well, we know theta can't be -1, or the R value can't be -1. So when theta equals 0, which theta being 0, if you picture a unit circle, 0 would be right here. It says -1. We're actually going to kick back to this point right here. Okay, so there's the point 0, -1. Now we're going to repeat this process with pi over 2. So we get -1 plus 2 times the sine of pi over 2, which is 1. So I've got pi over 2 is 1. There's that point. Plug in pi. We get -1 plus 2 times 0 again, and we get -1. But remember, pi would be over here, but it's a negative, so it's going to kick it back over here. So my next point is this way. And then we're going to go again, 3 pi over 2. 3 pi over 2, when I substitute this in, I get -1 plus 2 times the sine of 3 pi over 2, which would be 2 times -1, which is going to give me -3. And -3, 3 pi over 2 is this line right here. But with a radius of -3, it's going to bounce it back here. And now I'm guessing this 2 pi is going to kick me back to where I started. So if I plug in 2 pi, we get -1 plus 2 times 0, which is -1. 2 pi is right here, but I bounced that point back. Yep, and so we're back to where we started. And so you can see that this is going to start here, and it's going to trace this loop and work its way around, and then just keep going around and around. Now, would it be hard to get some of the curvature of this without graphing some intermediate points? Yes, it would. But the idea is that's how these are graphed in polar coordinates. You are not expected to know that. It will make some of our problems in our next lesson a little bit easier. But if you understand where the graphs come from, then when we need the points, it will be easy to find. All right, so you have a WebAssign that goes along with the polar conversions and equations, coordinates, and derivatives. And we'll see you soon.